As a surgeon, we come up with clinical needs and ideas of solutions all the time. Sometimes I tell people I can come up with a new idea every 15 minutes, but I just don't know how to create it or have the energy or time to bring it into practice.
Engineers are very versatile people. They are trained to work in teams, they're trained to listen. They're also trained to work with different disciplines.
The engineers sort of take it from being an idea into something that's really concrete.
So I'm working on a collaborative project involving University of Sydney students, academics and of course clinical technicians, and we're involved in creating patient-specific implants for skull injuries. We have developed a rapid templating technology which allows us to create patient-specific implants. Rapid templating is the creation of a two-part mould using 3D printing. In order to produce this mould, first we take the CT scans of the patient and we use these imaging to create a 3D model of the skull. We then use this to create a two-part template. We then provide this template to the surgeon who, during the surgical procedure, will place bone cement within the mould, compress it, like that, allow it to cure, and afterwards we are left with a patient-specific implant. The benefit of the process lies in the notion of surgical control. Now, often certain implants, especially more generically produced titanium, are quite hard to alter within a surgical setting, and often the surgeon doesn't have the tools to change this implant. Therefore, we needed a process which would allow the surgeon greater control over not only implant formation, but also implant alteration should the needs arise. The process as a whole is much faster, given that the rapid nature of 3D printing means that there's no machine setup, there's no need to send it to an external source. The machine prints the final template, which is then given to the surgeon for use. In addition, the overall cost of the procedure is lower than conventional titanium implants, given the relatively low running costs and material costs of the 3D printer.
It's been really exciting to work on this project with students and with clinicians and see not just concepts develop, but actually those concepts develop into real ways of helping patients that need the help.
As a student, it is very, very exciting to work on such a project which actually has real-world reach. We're actually interacting with not only real-world experts, clinicians, but also working with real-world patients to actually provide a tangible benefit.
The University of Sydney offers the premier biomedical engineering program in the region, which is the largest, but also one of the most diverse in that it offers 5 different streams: mechanical, mechatronic, electrical, chemical and IT. It also offers 5 different combined degree offerings as well, which is very popular for students who want to spend this front end of their career upskilling not just in one direction, but also in 2 areas or more.
Ultimately, I chose biomedical engineering because it's the perfect fusion between engineering, building, getting hands-on and making things that work, and human biology. So by fusing these 2 together, we're really creating a field on the cutting edge of both technology and human innovation.
Nothing pleases inventors and engineers and technologists more than being able to help the real world in a way that's not just generating new products, but actually is genuinely helping people.
This project has really allowed us to make a difference.